Hello, everyone. It's a pleasure to have Luke Postle today from University of Waterloo. He'll talk on further progress towards Hadwiger's conjecture. As usual, if you have questions, you can write during the talk, you can write it in the chat. I'll try to raise them to Luke, and then we'll have Q&A at the end of the talk as well, and some informative session, which will not be recorded. Luke, you can start.
All right, thank you, Liana. So thank you everyone for coming to this talk. So today I'll be talking about further progress toward Hadwiger's conjecture. So just to remind you of some of the history, I think you all know what coloring is. So K-coloring, we want adjacent vertices to not receive the same color. K-colorable if it has a K-coloring, and chromatic number being the smallest such K. Minors is the other major topic for Hadwiger's, and just to remind you, you get a minor from a subgraph by contracting edges, but it's going to be more helpful if you're not familiar with this to think of them as models, which is equivalent. You have a graph H, a model of H in a graph G is a collection of vertex disjoint subgraphs and connected so that if there was an edge in the original H, then there's some edge with one end in HI and the other in HJ. So here is kind of the minor view where you're doing the contraction. Here's if you pull back, you get this model view. So really when we're going to build KT minors, we're going to build KT models. And it's not hard to see those are equivalent. But the question is, do coloring and minors have any relation? So you probably all know Hadwiger's conjecture, so this seems obvious. I just want to stop and say it's not really obvious, right? I mean, coloring is about partitioning into independent sets. And minors or models is about finding kind of connected subgraphs with lots of edges between them, right? These are not really dual in any sense. These one's concerned with, being up into independent sets, and the other's finding structure inside that's highly kind of connected or adjacent. And it's not clear there should actually be any relation. And so I think from that view, it's really surprising that you have this Hadwiger's conjecture from 1943 that every graph with no KT minor is T-1 colorable. But not only is there a relation between these two concepts, but there's a very strong relation because kind of T-1 would be best possible because you could have KT-1, of course. And what was known, you probably all know that the Hadwiger and independently actually Dirac had proved it for T at most 4, right? For T in 1 and 2, it's trivial. For T equals 3, it's just saying if I don't have cycles, then I'm 2 colorable. So that's easy. 4 was a little bit harder, but also relatively easy. While as 5, Wagner had actually shown before Hadwiger that it's equivalent to the 4-color theorem, which was only proved by Apple and Hawken in the 1970s. So, this already is a generalization of the 4-color theorem. So I think that's why a lot of people like Hadwiger's conjecture, is because it's kind of a vast generalization of the 4-color theorem, and the 4-color theorem is very hard and open and a central problem. And so this seems very hard. But there is one other case that was shown, and that was by Robertson, Seymour, and Thomas, who showed that the T equals 6 case is actually equivalent to the 4-color theorem. So they reduced it. Now, that proof doesn't use computers, but it does use maybe 100, 150 pages of math. I mean, you can check it by hand, but to reduce it. So, and then you still need the 4-color theorem as a black box, which is kind of obvious because you could have apex graphs and you need to show those are 5-colorable. So you need the 4-color theorem. But they did that in 1993, and that's basically where we've been at for cases. T at least 7, C equals 7 seems very hard, and anything beyond just even harder. So maybe it's better than to ask about general bounds instead of what cases have been proved. So there's kind of the linear version of Hadwiger's conjecture, right? It's not too hard to show that planar graphs are 5-colorable, 6-colorable. So if we relax that exactness, if we ask for, is there some constant for every graph with no KT minor is CT colorable? Is it kind of, can we get linear, 2T, 3T? That would be very nice and in the spirit of Hadwiger's. And this was conjectured by various people. And that's still also wide open and seems quite hard. What is known for general bounds? Well, you can, instead of really using color, you can just use the structure of KT minor free graphs. So a graph G we say is G degenerate, if ever a subgraph of G is a vertex of degree at most D. And a simple greedy algorithm shows that if you're D degenerate, then you're D plus 1 colorable. So it's natural to ask what is the degeneracy of graphs with no KT minor, or somewhat equivalently the kind of the average degree or maximum average degree when you exclude a KT minor. And there is actually something. Kostochka and Thomason in the early 80s independently had shown that every graph with no KT minor is O T root log T degenerate, and hence T root log T colorable. And that's actually best possible up to the order. And actually, Thomason in 2001 have found the exact constant that goes there. And so you get this bound just from the degeneracy. So just because you know that KT minor free graphs can't be too dense, you get some natural coloring bound, but there's not much coloring there, right? It's just applying greedy with that degeneracy bound. And that was the state of the art until just last year. So, you know, for 30, almost 40 years, this is where we've been stuck. We can get this T root log T bound, but that was about it. Now, there had been over the years, Thomason and then Wood, and then my student Tom Kelly and myself had improving the constant factor a bit, but that we hadn't actually, no one had improved the overall kind of bound, the order of the bound from that T root log T. Until this very beautiful paper by Sergei Norin and Zizhia Song appeared on the archive in the fall of 2019. And they showed that for every beta, at least 0.354, every graph with no KT minor is O T log T to the beta colorable. So they got down from that square root, that half, now down to 0.354. So the first real progress in the order. And I'll be going through that proof a bit. So I saw that and I was able to improve on one of their arguments there and show that for every beta greater than a quarter, you can get T log T as a beta colorable as well. So getting that down to a quarter. And that was also last fall. And we ended up merging our efforts. So I present these as two different things, but now it'll be one paper. But I just want to make sure they get the credit because they had really come up with this nice strategy for attacking Hadwiger's conjecture. And I'll be going through that. And I've improved one part of it, and we'll also be talking about improving the other part today. So that was the state of the art kind of last year. We wrote up the paper and submitted it. And then this year, during the pandemic, I thought about it some more. But first, I'm supposed to mention generalizations, sorry. So two other things we did in the meantime. So one generalization of Hadwiger's conjecture. It's a little weird to ask about generalizations because we haven't proven it, but people have done this. One is odd minors. So a graph G contains H as an odd minor if a graph isomorphic to H can be obtained from a subgraph G prime of G by contracting a set of edges forming a cut. So it's a special kind of minor. And Gerards and Seymour, at least by the early 90s, asked kind of the odd Hadwiger version. So if every graph with no odd KT minor is T minus 1 colorable, is that true? And the best general bound was by Gieling, Gerards, Reed, Seymour, and Beta, and they had shown this T root log T. So you don't get the degeneracy bounds because bipartite graphs have no odd K3 minor, but they could have arbitrary degeneracy, but you can make arguments still to get around that, and they then show this T root log T bound for the odd case as well. And that was the best known bound until Norin and Song improved it to this beta greater than a quarter. So using the additional work, but they'd extended this quarter result then to also work for odd minors. So that was very nice. And that's actually the best state of the art. So what I'm going to talk about today doesn't work for odd minors. It fails in some key places, it seems. So this is currently the best known for the odd minor conjecture. Similarly, there's the list coloring version. So graph G is K-list colorable if for every assignment of list of colors to the vertices, you get a coloring from those lists. So also very well studied. Now you could ask about the Hadwigers for list coloring, but actually this is just false. So Margit Voigt, she had shown in '93 that there exists a planar graph that's not for list colorable, so hence list Hadwigers would be false. You might wonder, maybe it's just off by one, so Thomason had shown they are 5 list colorable. Maybe you could hope, but actually Barat, Jaurès, and Wood in 2011 had extended that construction to show that there are graphs with no K3T plus 2 minor, which are not 4T list colorable. And so you can't really do better than 4/3 as a ratio, but it kind of conjecture that maybe you could do 3/2 or at least linear list Hadwigers would still be open. And again, the Kostochka and Thomason bounds, degeneracy implies T root log T list colorable. So that was the best known bound, again, for a very long time. But then with Sergei, him and I were able to also extend that quarter result with some extra new ideas to work for list coloring. So the T log T beta list colorable for every beta greater than a quarter. And that's where we were at. So, we have this nice thing. We had it for coloring, extended to odd, extend. You can't do both extensions because, again, bipartite graphs still have odd minors, but they could have high list chromatic number. So you can't get both, but we could get kind of both extensions. And that was very nice and pleasing, and that was the state of the art for those. But now, returning to what I wanted to talk about today was this further progress. So not list or not odd, but just the original conjecture. What can we do? Well, actually this summer I came up with a proof that for every beta greater than 0, every graph with no KT minor is OT log T, beta color. So we can get that quarter down a bit. We can get rid of that log factor. And then it becomes very important. So what is this extra term? And if you do more work, and I'll talk about it a little bit later where this comes in, but I won't go through the details really that in this talk. More specifically, you can work and push this and get to T log T to the 6th colorable. So you get the log down to log. Now it's a power there, but that's where we're at now. So this seems, yes, we're getting this log realm. And you'll see there are some kind of natural barriers to I think even go, maybe you could move the 6 down, but you're going to find some kind of natural barriers around T log T as to why it will get harder. So that's the state of the art. If there aren't any questions, I will continue. So that was the introduction. Now I'm going to be talking about this proof from the fall, this proof with Norin and Song and myself, and going through that quarter result. Because it's important to understand some of the concepts if we want to do the general, this further progress. So one thing is that we can color small graphs. So how do you color small graphs? Well, Duché and Meniel already in 1982 had shown that every graph with no KT minor has an independent set size at least V over 2T minus 1. So kind of, you would expect if Hadwiger's was true to find an independent set twice that of V over T minus 1 by taking the largest color class. And here they can kind of get half of that. So kind of the independent, a linear independent set version of Hadwiger's. Woodall had kind of extended that to show that actually you can even just get a subset of half the vertices with chromatic number of most T minus 1. You can just iterate those results then to get a very nice bound in the chromatic number for small graphs. So here we're talking very small, like T polylog T size. But if you put that into here, you get T log T type chromatic number. So we can kind of just by pulling out independent sets, very kind of greedily color very small graphs. But why is that important? Well, those graphs that matched up with the Kostochka and Thomason bounds that showed those are tight, those are actually small. They're random graphs on like T root log T vertices. And this result tells you, well, those actually we can color pretty decently. So we don't really have to worry somehow about those kinds of obstructions anymore. So we're going to use this as a black box for coloring small graphs. And I'll just point out that Reed and Seymour had actually extended the Duché-Meniel result to fractional coloring and shown fractional, like linear Hadwiger's for your most 2T minus 1, which is very nice. And so that's what we're going to need there, the small graphs. And then we're also going to need a density increment theorem. So let the density of a graph G, denoted dg, just be the edges over the vertices. So this is kind of half the average degree. If you want to say average degree, that would also work here. But here's a question. When does a graph of density D have a minor of density capital D? So some bigger D, right? This would be useful. We don't, maybe we're trying to T color so we know we have density T, but if we could get up to T root log T using Kostochka and Thomason, then we could convert that to a KT minor. So increasing the density would be a nice goal. But is there some obstruction to this? Well, yeah, small graphs come up again, right? Because if you had density big D, you need at least big D squared edges. And if you had density little d, well, if you had smaller than that, if you had smaller than big D squared over little d vertices, you just wouldn't have enough edges to possibly make such a minor. So that's one obstruction. And of course, you could just take the disjoint union of such kind of dense small graphs, and they would also be an obstruction to getting a denser minor. So this is kind of the natural obstruction, and the question is, is this kind of the only obstruction in spirit? And so there's a theorem that says yes. So for every s at least one, there's some gs. If your graph, let's say, has at least some edges, so d is greater than 0, and you let d be s, big D be s times the density, then you either get one of two outcomes. You either get a minor of the larger density, or you can find a subgraph H with vertices at most kind of this d squared over d, but times this gs, and where the density is also pretty large, kind of verifying, but by again dividing by gs. So you should think of gs as a kind of error term here. So, g of s was 1, this would kind of be exactly what we want, but maybe we'll pay a little bit of an error term to get this. So kind of an approximate reason why you can't get a denser minor is these dense small graphs. And so what is GS? This doesn't make any sense until I tell you what GS. Well, Norin and Song had actually shown that you could take G of S to be S to the alpha for any alpha greater than 0.7095. And they used that in their proof to get the 0.354. And then I had improved this to G of S being S to the alpha for any alpha greater than 0, and that's what gives you the Porter proof. So that's very nice. And more specifically, you get something like 2 log S to the 2/3 plus 1 there, and that would then translate to a 2 log T to the 2/3 in the Hadwiger bound. But then that became important to improve the GS after I had made this breakthrough in the summer. And so actually I went back and was able to improve it even further and get it down to 1 plus log S to the 6th. And so that's actually what gives you the log T. Because we're going to be applying this with S being like root log T. And so you're going to get log T to the 6th showing up here. And that will come in very importantly into it. So this is actually the current bottleneck for the bounds, is if we could improve this GS. We could get that 6 down to a 5. I mean, it could be 1 plus log S. It could just even be maybe a constant for all we know. So I don't know what the appropriate lower bounds are there. It's actually too hard to improve them. So that's where we're at. So we're going to use this as a black box. How are we going to use it? Well, let me go ahead and tell you. So let f of t be, this is just some number, 3.2 square g 3.2 root log t, but that's, now we know that's on the order of log t to the 6th. And here's the idea, is if a corollary of this density increment theorem is if you had a graph with density at least k times f of t and no kt minor, then you contain a subgraph that's small. So the number of vertices would be t f t log t, and the density would be at least 2k. So you tell me what kind of density you want, 2k, and if your original density was times f of t of that, then I can get you a small dense subgraph. And why do I use 2k here? Well, if you invoke Moder's theorem, if g of h is at least 2k, then you can get a k-connected graph as a subgraph. So we could actually use that and actually replace it and say, no, we can even get a k-connected graph. So you tell me what connectivity you want, and with a little bit like a log t to the 6th error term, I can get you that while keeping it small, in the t polylog t realm, which is nice because those are easy to color. So actually that's what we really do, is if you have a graph with no kt minor and the chromatic number is at least kft plus 2t log ft plus 6t log r, you can actually find r vertex disjoint k-connected subgraphs that are all small. So you just pull them out one at a time, and they're small, so they're easy to color, and then what remains, if it has low density, would be easy to color. So actually, you must be able to keep pulling out small, dense subgraphs. So what good are small, dense subgraphs? Well, to do that, I need 2 more concepts, and these concepts will come back in our further directions proofs, but maybe you've seen them before. So one you've probably seen is linked. So we say a graph G is k-linked if for any set of vertices S1 up to Sk, and here's a picture, T1 up to Tk, there exist internally vertex disjoint paths Pi from the S. So this is like Menger's, like connectivity, except here we have an order. So S1 needs to get to T1, S2 needs to get to T2, etc. And here I will even allow you the S's and T's to be the same as long as they're internally vertex disjointed. It only makes a difference in constant. And importantly, Bosch and Thomason in '96 had shown that if you're linearly k-connected, if a graph G, so here they had shown like 22k, if a graph G is omega k-connected, then G is k-linked. So linear connectivity is enough at a constant vector to give you this additional ordering property to do linked. Now, another concept we'll need, though, which I gave a name to in this paper, but which Norin and Song had kind of used and introduced, I'll call woven. So a graph G is AB woven if we're going to have 3 sets of vertices. So here's a picture, R, S, and T. So S and T are old linkage, so we want to find paths between them, but R1 up to RA, will be, we want to find a KA model, or minor, rooted at R. And what rooted means there is just every vertex of R is in exactly one part. So we have one part of the minor having R1, one part having R2, and so on. So we kind of get, so when you contract down, you'll see the R's on the parts of the minor. So we can build the minor on a rooted set, that's the A, and we can still get a linkage S1, S3, T1 to TB as needed. And the theorem is that Norin and Song had showed that actually using kind of the Bosch Thomason machinery, it's a nice combination. They've shown that if you're omega A root log A plus B connected, then you're AB woven. So this implies the Bosch Thomason, but also notice it also covers the Kostochka Thomason, right? If you're that level of connected, you're that dense, so you get a KT minor, but actually it's kind of more than that. You get rooted minors, so you can build on specific vertices, and you can also preserve, get paths, get linkage at the same time. So that's very nice, and we'll use that. And now that I have those machinery, now we can just go about building our miner for the old proof. So let's build our miner in the case when, you know, our chi was t log t to the quarter times, say, this f of t, this kind of error term. To do that, we'll let y be log t to the quarter and x be t over y. And then, well, by work of Kobayashi, actually, you can assume the graph is highly connected. So just at a constant factor, xy squared times some ft connected. Now, then what do? If you're highly connected, you can use this density increment corollary to extract lots of subgraphs. And all very connected. So only at the cost of the ft, you can get them xy squared connected. So I'm going to call them h0 up to hij. So here's kind of a picture. So you have one hub, h0, and then you'll have kind of rows and columns, the hij where I is less than j. And what we do then to build our miner is in h0, we'll choose kind of s's, so big blocks of vertices. So these will be sijks. They'll be in the si's, and then inside each square we'll take a tij. And the idea is that since g is xy squared linked, we can just link all of these vertices sij to tjik. So we can get these big blocks. So the important thing to note is kind of, you know, S1 and S2 are both going to H12, you know, S1 and S3 are both going to H13. So the idea is kind of, I want to split up my miner into these chunks of size X, and I want them to build complete miners in pairs. And that's what these squares will do. So how do we actually do that? Well, now that we have these paths, we can finish by, in each little square, we'll weave a model, a K2X model on the TIJs. And it's important, though, while we preserve P. So we can do this weaving because we're xy squared connected. So we have this by the Norin song woven theorem. We can do that while even preserving an xy squared number of paths. And do we have that many paths? I'll just point out, so you don't have to preserve every path. So if you look at kind of the left side of my picture with just the blue, then you see there's two paths there, and one outside. We don't care about that one because we don't have to preserve it. It's fine, it's outside. But the two inside, we don't actually need to preserve all in and outs. We just need to preserve from the first in to the last out, right? We just need to preserve the overall path. So that will, so really for each path, you only need that to preserve in one way with these, and I drew them in green here. So you do that, and you just work through each square, and you just weave a model while preserving that overall path structure. And then finally, you go back to the hub, and you just link up all of kind of the SIJK. So S1 wanted to go through all of its row, you can link it up, and now you'll get actually a complete miner in this way. So we use the hub to do the linking, and we use the little squares, the little small subgraphs to build little complete miners that we grow into one giant one. So that was a sketch of that proof. Now I'm going to try to, now that we've talked about that, how do we improve on this? How do we build the miner better? So if there are any questions, I'll move on to this further progress. And the key is we're going to break into two cases. How do we do that? Well, how do you build a miner? How do you build a complete miner? Well, here are two additional ways to. So in the last step, we just kind of built it all at once, right? We found lots of little miners, we connected them to a hub, we linked, we just built it, did it all at once. And I'd like to say there's actually kind of two nice additional ways to build a complete miner. The first way is recursively. So actually, kind of if you could build 3 K2T over 3 models at the time and link them, then this would work, right? So if you were trying to build a KT, you could divide it into thirds and just try to get a complete graph on each third. And then if we could link up those miners, we get a nice KT miner. The other idea I want to suggest is sequentially. Let's successively build up a KT model, but only adding square root log t new vertices at a time. So that's kind of like the old picture where we try to add, only one, maybe, row or column at a time. Just kind of, let's build up just kind of successively a little bit of the miner at a time. So these are kind of two different ideas. And how are we going to use them? Well, the issue is in each case, we need, either if we're doing recursive or sequentially, we're going to need many large, highly connected subgraphs. We're going to use linking and weaving to do this, right? Recursively, we're going to either need lots of levels of vertex disjoint, highly connected subgraphs, and many levels of them, so they're going to have to be large as you're going. Or sequentially, we're going to kind of need nested many, square root log t, many such graphs, highly connected as we're going. And the issue I kind of got stuck at is, well, what resource do we have for forcing large graphs, right? So, I mean, this small density increment theorem was enough to go find one little small graph, but how can you force in other levels? And the answer is chromatic number itself, right? So in the proof for the one chord I showed you, we actually don't end up using coloring that much, right? We use coloring to color small graphs, but after that, it's mostly this density increment and weaving and linking, and we don't use much chromatic number. So actually, let's use it again. Let's use it as a resource to force large graphs. And even more, can we also guarantee high connectivity? So actually, this is a nice breakthrough result by João and Norin from just this year. So Sergey had asked this question actually at the Banff conference, and they ended up answering it very quickly with a very nice proof. It goes like this. For every positive integer k, if G is a graph with chromatic number at least 7k, then you get a k-connected subgraph H with chi of H being at least chi of G minus 6k. So what is this theorem saying? It's saying, you know, if you have decent chromatic number, you can exchange just a bit of that chromatic number for connectivity. So if you want me to be k-connected, I can find a subgraph that only loses 6k colors in the chromatic number and is actually k-connected. So you can exchange. So here, if we're using chromatic number, you know, we don't need a lot of connectivity if we build the minors a bit more smartly. And so we'll do that. We'll kind of exchange a bit of the chromatic number for connectivity as we need it using this theorem. So if you haven't read their paper, it's on the archive. It's just very nice. It's just a couple pages. It's kind of from the book proof of this result. And so it's going to be the key to our results here, to use this as a black box when we need to get the connectivity. And so actually you could use this one instead of the Karabayashi result for the quarter proof as well, but it wasn't around at the time when we had done that. Okay, so now let's maybe use this. So how do we do it? So here's the key concept we came up with, or I came up with. So a graph G is S chromatic separable if there exist two vertex disjoint subgraphs H1, H2 that have chi of HI at least chi of G minus S. So right, let's try to think, can we kind of split up the graph? Can we find two disjoint subgraphs with high chromatic number? That would be very nice. We'll call it S chromatic separable then, and S chromatic inseparable otherwise, if we can't do that division. Now, this is a little bit silly, right? Because you could always split a graph into two subgraphs with like roughly chi of G over 2 chromatic number. But here I'm going to be asking for higher. Like you only lose a very tiny bit compared to the overall. So you're thinking chi of G is much bigger than S. You know, can I find two really high? Now you can't always do this, cliques, right? You can't do it in cliques. But we're going to handle these two cases separately. What do I mean? We're going to consider whether we're kind of always separable, which will just be separable for high chromatic subgraphs, or inseparable. So in the always separable case goes like this. We have a lemma that says, if your graph has chi at least S log t, and every subgraph with at least chi being half of the original is S chromatic separable, then we can get a KT minor. So if as long as we're kind of always separable and have high chromatic number, I'll build a KT minor that way. In the second case, it's the inseparable. So let S be of omega t log t if you're actually S chromatic inseparable and chi is at least t ft plus log t. So that's where the ft comes in, that log t to the 6th. Doesn't show up in the always separable, just here in the inseparable case, then we'll get a KT minor. So now if we just put these two lemmas together, then actually you can just prove the theorem, right? Because, well, you let S be, you know, t log t, say, then as chi is at least t log t to the 6th, we'll get the always separable case would work. So actually that must fail. There must be some subgraph that's actually high chromatic number and inseparable. And then you just apply the inseparable case lemma to that subgraph. And that works because you're at least, you know, TFT plus log t in chromatic number. And then we get a case. So it's just dividing into these two cases, always separable or inseparable. So that's the big idea for the overall. And then I'm going to go through how to build in each case the minor. All right, so big takeaway here is we use chromatic number as a resource, and we split into these two kind of cases, separable and inseparable. So what do you do in the always separable case? Well, I've already kind of primed you. We're going to use recursion. So we're going to build the minor recursively. And actually, I'll show something a bit stronger. So let A equal T and B equal 0 will actually show your A0 wovens. That would be T0 woven. You can get rooted minors even in this case. And how do you do that? Well, let me walk you through it. So we have this graph G, and let's just assume that G is already decently connected by the João and Norin theorem. But then because it's separable, there exist two disjoint subgraphs, so I'll call them H1 prime and H0 prime. It's again still a pretty large chromatic number. But now 2 isn't what we want, right? We wanted 3 for the thirds. So you take H0 prime, use the always separability. You say H0 prime is chromatic number at least half of G. So then you'd actually be able to find two high chromatic subgraphs of it, H2 prime and H3 prime, that have only lost 2s from the original. And then you apply the Generalizations theorem to H1 prime, H2 prime, H3 prime to find H1, 2, H2, H3, which are highly connected as well. So you can get K-connected subgraphs with, again, not losing. If you think S and K are kind of small, you don't lose too much. So we can find 3 still very high chromatic subgraphs that are K-connected inside of G. And now we're going to go ahead and build it recursively. So let's even assume that R is given to us, so we need to build a rooted minor on R1 up to RA. How do you do this? You just split it into thirds. You have R1, R2, R3, you just split it into thirds, and you think of those as your S's. And then inside H1, H2, and H3, you take sets of vertices called T. So T1, T2, T3, and then you, since you're highly connected, you could assume you're 2A linked by Thomason, and you'll find lots of paths. So you kind of have R1 and R2 go to T1, R1 and R3 go to T2, and R2 and R3 go to T3. In exactly the manner I described here. And I just want to note, I kind of drew the last one crazy to really hammer home the point. These paths don't just have to go to T1 or T2, you know, they can wind through. So they can wind through the rest of the graph, you know, the ones to T3 can wind through T1 and T2. They can do whatever they want, but we're getting kind of, you know, each pair of thirds to its own special subgraph. And then what do? Well, now we just weave, right? So we're going to recursively weave inside of H1 a K2A3 model rooted at the TI. So that's why we needed the rooted, because we need it. Now it's actually the TIs are fixed. There's no choice. So now we actually have to work in more general paradigm of woven. And we also have to work on woven because, again, we could have these paths, you know, these paths P that we need to preserve. And so as you go down, we're going to repeatedly apply this recursively. And as we go down, we need to always preserve our ancestor paths. So now we'll do this again to inside H1, we'll get new paths, and inside the 3 inside there, you'll need to keep preserving upward. So let's go through the numbers for this. So inductively, you just kind of do this each time. So at step 0, we have an AI and a BI. So here we had T and 0. We need to show woven. Well, the next step, we need 2/3 T for the A's, right? That's the complete minor we need. But now we need to preserve those paths. How many paths were there? There were 2A0, right? Then we had, if you go count it, you needed 2 because each one went to 2 different subgraphs. And then in the second step, when you go to the next level, you get 2/3 squared, and so on. You get 2/3 to the IT. Whereas for the B's, you have to preserve, again, all ancestors upward. So you need 2A0 plus 2A1, and more generally, 2 times the sum of the A's before it. Now, luckily, the A's keep getting smaller. We're building smaller and smaller complete minors, so we have fewer and fewer new paths to preserve. And so actually this forms a geometric series and can just be upper bounded by 6T. So we only have to preserve 6T paths, and if we keep doing this until I reaches about omega log T, AI will get down to less than T over log T, or T over root log T, and then you can just apply that Norin-Woven theorem, and you're done. Because then your connectivity would be at least, A square root log A plus B, and you'd be done. But the important question is, how much chromatic number did we end up using when you're doing this, right? Because we need to make sure we only use up half, because T is the always separable. Well, each step we use 2s plus 6k, and there's omega log T steps, and K is, we only need 6T connectivity throughout all these steps to end up getting the paths, or omega T connectivity. So in the end, you need like T log T there, and you also need S log T. So that's bigger than log T, S log T suffices, and you prove the always separable case. So that's the always separable case. We recursively weave, right? It's very nice. You just split into thirds, you pair up, and you use as a base kind of case that Norin-Woven theorem. What about the inseparable case? Well, here's the plan. The plan is to build a KT model, again, in a number of stages, right? So I said sequentially. So the always separable was the recursive idea. Here we're going to do sequential. So we'll build a KT model in y equals square root log t stages. So here I changed it from the log t to the quarter, kind of we had before, because now we'll need actually the square root log t. And where at each stage we're ensured that a set of x equals t over y new parts are adjacent to every other part. So we're going to have y stages, and each stage will build t over y new parts. And to do that, it's going to be helpful to come up with the following definition. So we'll say a model of H in a graph G is tangent to a subgraph G prime of G if for every I, then you end up with exactly one vertex of that part in G prime. So you have G prime, and we'll say the model is tangent if for each part has exactly one. So kind of it's tangent to the subgraph. It's each part is intersects the subgraph, but only in one. So there's still a lot of the subgraph to work with. And so the idea will be we'll try to use this tangency to when working on these new parts. So let me go through that a little bit more step by step with the plan. So again, here's our goal. For every I and y, we'll extend a KIX model, HI, to a KI plus 1 X model, HI plus 1. So we'll add in these X new parts adjacent to all of the HJs while preserving all previous adjacencies. So we'll do that. So we're going to, each time we're going to be working in a subgraph GI, and then we're going to ensure that we don't use up too much of the chromatic number inside GI, so that the model leaves you with chi GI minus HI plus 1, this extension. There's still a lot of chromatic number left over. And then we can use the Girard-Narayanan theorem to find a high chromatic, high connected subgraph GI plus 1 that's disjoint from the HI plus 1, right? It guarantees us, we can trade a little bit of that chromatic number to still have high chromatic number, but also good connectivity. And then what do we do? Well, then we'll try to make our model tangent to GI plus 1. So we'll somehow extend it even further and try to make it intersect in only, each part in only one vertex in that GI plus 1 to start over. So we kind of, start with our big graph G, we'll call G0 or G1, and then we kind of build a bit and we shrink the graph, right? And each step, so we have GI, and we'll still find inside, we'll build a bit of the model, and we'll still find inside this kind of high chromatic, high connected subgraph. We'll get the model there, but not too much there, this tangent idea, and we'll keep going. And we'll do that in the steps. So let me go through, and there's pictures coming each of these kind of steps, more one at a time. So let's go through the first step. How do you get there, right? How do you extend the model? Well, since HI is tangent to GI, let's call these vertices in the parts the UMs. So V of HM intersect V of GI. And now here's a picture. So we have these U's. By the density increment corollary, we mentioned we can extract, because you're a kind of a high chromatic, high connected subgraph, you can extract, there's high density, lots of vertex disjoint omega T connected subgraph. So I'll extract an H0 and I'll extract HJI plus 1s. So this is to reminisce you about the old plan, right? So this is basically the old plan, except we have these U's, kind of the old part of the model we'll have to worry about. We'll have a hub H0, and we're only going to need one column of these small subgraphs, because we're only building one kind of column at a time. And in HJI plus 1, again, we'll choose vertices TJI plus 1, not drawn, inside each one to build complete minors on. And then what we do is, actually here we don't even have to use linked, we can just use Menger's theorem to connect up the U's and the T's all to that central hub H0. And again, the picture's a lie. Those paths can go through the H's, the other H's, and the rest of the graph, but they'll get to H0. So Menger's theorem, we connect everything centrally to the hub, and then it's the old plan. We just, inside of H0, you're decently linked, so you can link up the U's to their kind of where they need to go, their new adjacencies that they need in each of the small subgraphs. And the new parts we're making, that's kind of depicted on the bottom there, you just kind of link up each new part so as to make sure it has all the necessary adjacencies. And are not depicted here because it makes the thing too complicated. Inside each HI, then we go through and we weave. So we preserve these paths as depicted, and we weave a complete model on the TJs. TJI plus 1s for each one successively. And now, so it's really just the same old plan. We're just making sure we link in the U's, which are the old parts of the model, and we build kind of a new column of the model. So that's really, if you understood the old part, it's basically that just on one row or column. The issue is, how do you get onward? You know, let's go to the other steps. Do we have enough large, you know, is there enough chromatic number left, right? Do we use up too much? Well, think about what we did here. So we had chi at GI was large. What did we lose? Well, we have all these small graphs, right? We had all the U's, the H naught, the HIJs. So let J be the union, say, of all that. It's all small. So by the small graphs lemma, you can just have chromatic number. You're using the most T log log T colors for that, for the small stuff, right? There's only, you know, TUs, and there's only log T, you know, H's. So, and they're small, so you don't use too many colors on that part. But what about the paths? What about these paths we made? Well, let L be the union of these paths. The key is you just assume the paths are induced, right? Just makes them shortest to there. So, you know, skip over if you can, make them induced. And then there's only 3 T paths. So then you end up with chi of L being at most 60. So the paths, if you do it smartly, don't take up too much. The small graphs don't take up too much. So in this one step, the chi GI minus HI plus 1, you only lose, you know, on the order of T log log T colors. So that's pretty fine, at least for the first number of steps, and we can keep on going. The issue is really, how do you do step 3? How do you get, so you have high chromatic remaining, you know it has a high connected subgraph by Norin, and the question is, how do you get there? So here's option 1. So if we knew where we need to go, you could kind of argue, could we use Mengers to find the paths from GI plus 1 back to the hub and then use the hub to do the linking? Well, this is just not going to work. That's just bad. You're going to intersect the paths, right? There's no really guarantee that our paths P haven't blocked off like the hub from the GI plus 1s, or have blocked off each other from the GI plus 1 from this future, right? So it's kind of, you should think we've had the past model, we're linking it into the hub, there's the present stuff we're building, and GI plus 1 is kind of the future. And the issue is, you know, we maybe can't get from the future back to the hub. So maybe you say, okay, now we know where we need to go. Option 2, this seemed like a nice idea to me, was let's start over. Let's get the paths from GI plus 1 to the hub H0 while constructing those pieces. You know, now I know where we're going to go, so let's go ahead and just force those to connect to the hub at the same time we're doing this. But if you think about that, you're going to realize that's also bad. It just doesn't work, because if you have to start over, there's no control of the paths. There's no, it may be that the new path P would intersect your nice future, your GI plus 1, destroying both its chromatic number if it uses up too much there. Also the tangency, because now it could intersect more than once. So somehow, this was where I got stuck for quite a while. You know, we know how to build one step, but how do we get to that next step? We couldn't get the next step to come to us if we've already built the P. And if we start over and try to do them at the same time, then we lose our grasp on the future. You lose your tangency there. And so this is where it just was slippery. And the solution is quite nice here. You ensure redundancy, option 3. So this actually works. It's crazy. So you want to build these paths P, but you also want connections from GI plus 1 back to the hub. You just kind of double everything. So instead of making those nice paths, as I drew in the last picture, these paths P, you instead actually make double of them. So for each one of those paths you see, you know, make 2. So have U1 have 2 different paths. Have U2 have 2 different paths. And the same from the 8. Make double the paths and add kind of redundancy into the picture. And then you can use Mengers to get, again, kind of a double the paths from GI plus 1 to H0. So instead of just making one path for each, you kind of make double what's required. So you double from the future and double kind of from the past and present. And then a simple application of Mengers' theorem shows that actually then you can convert that to get a single copy of both. So maybe that's a not so well appreciated thing, but yeah, if you have double the paths from A to B and kind of double paths from C to B, you can get the single paths. And so we can kind of get them to all meet in the hub in the middle, and that part will work. But now we run into so think about that, but now we run into a different issue. So we've solved with redundancy how to make it tangent, but I kind of lied about step 2, right? Is chi really large enough? Because no, I mean, we lose T log T at each step. That was fine for the first couple steps, but there are square root log T steps. you would need t root log t color. That's way too high. So what do? The solution is you rebuild the minor at each step. So this is nice. Because what does the minor need from each HI, right? I think of these parts of the minor, the HI. What do they really need from the minor that we're trying to build? Well, you want to keep the tangent vertices, right? You want to keep that one vertex in the future to keep building. But besides that, you really just want to keep your connection to those small graphs. You just want to, right? You went to some of these TIJs, you just want to keep those because that's what gets you the adjacencies, these small complete minors. And is that enough? Well, yeah, you can just rebuild the minor with this nice little lemma. So here's a lemma. If G is a connected graph and you have a subset of vertices, think of them as the terminals. So you have these terminals S. You want to find an induced connected subgraph H of G and kind of enlarge the set of terminals to S prime. That's not too much larger. So there's only going to be 3 times the size of S, with the property that what remains in the subgraph has chromatic number at most 2. Can you do this? Yes, it's a simple kind of inductive proof, but it's nice. So it's kind of saying, we had only these small graphs to really worry about, these small terminals that I have to preserve. Well, this lemma just says, well, actually, I can just triple kind of what's deemed important, and then actually the rest are just kind of disjoint unions of paths and have small chromatic number. And so combined, you have small chromatic number from the important stuff because they're small, and then you have 2 from the rest in each part. And so if you apply this lemma to each part of the minor, and again, the S's will be at most like t poly log t, so here t log cube t say, you'll get a new minor. You've rebuilt the minor. It's actually a subgraph of the old thing, and it will be tangent to gi plus 1 because we'll kept the tangencies. And the new chromatic number, you'll actually only lose t log t. You'll lose kind of 2t from the paths from the lemma, and then the t log t coming from the union of all the small graphs because the union is very small. And okay, are we done then? Well, there's one last bit, right? So we use redundancy to meet the future. We read this lemma to rebuild the minor to make sure we actually don't lose too much overall. Like we don't lose too much in each step. We actually rebuild it so to not lose too much overall. The issue is, what then? Well, by the Girard-Norin theorem, there'd be a subgraph gi plus 1 prime that's disjoint with high chromatic number, right? So you know what remains once you've rebuilt has high chromatic number. So you have also a high chromatic number in a highly connected subgraph. So I'm supposed to say highly connected there. But the question is it tangent? So we rebuild it, we refind it, but we were tangent to what we thought was the future, right? We had a gi plus 1 in mind, but then we lost too much chromatic number, so we rebuilt and we kind of used their theorem to find perhaps a different thing. Is it the same? Is that future the same one we were tangent to? No, maybe not. There's 2 cases. Case 1, if our old gi plus 1 and our new gi plus 1 prime have at least k vertices in common, then you just take the union of the 2. Gi plus 1 is k connected, gi plus 1 prime is k connected. If they intersect in at least k vertices, the union is k connected. There'll be and then they'll be tangent to this new model. The model was disjoint from everything but those tangent vertices in the old gi plus 1. So that's kind of a nice idea. If the old future and new future overlap too much, you just kind of throw it all together, and now I'm tangent to that, and it has high chromatic number, and that's great. The other case is that they're actually kind of disjoint, meaning they have less than k vertices in common. Just delete the common vertices, say from gi plus 1 prime, and you'll get 2 vertex disjoint subgraphs, both having large chromatic number, right? Because gi plus 1, it only lost an additional t log t from where we were, so that has high chromatic number. And we rebuilt to make gi plus 1 prime also have high chromatic number. So now we find 2 vertex disjoint subgraphs that don't lose too much from the original, and that's actually separable then, right? So we hadn't used the inseparability at all throughout this case, this proof, until this very last moment where we find these 2 high chromatic subgraphs, and that gets you a contradiction that you're actually t log t inseparable. So just in summary, so that concludes the proof. In summary, we proved that for every beta greater than 0, every graph with no kt minor is ot log t beta colorable. And the key was to divide into cases this always separable or this inseparable, using chromatic number as a resource. and building either recursively or sequentially the minor. And with the better density increment theorem, which again I don't have time to talk about today, and tell you the proof of that, and also how I improved on it and things, but if you just slot that into this, you end up with OT log to the t to the 6th colorable for graphs with no KT minor. And so then in conclusion, yeah, there's just lots of future directions we can go, but I think I'll stop there. Thank you.
Thank you, Luke. I suggest everyone unmutes themselves and we give a round of virtual applauses to Luke. Okay, questions? Luke, do you want to say more about this future directions?
Sure, yeah, I could say, so I'll just say a little more. So yeah, again, can you improve the density increment theorem? That's the current bottleneck, right, for the whole proof, for improving the bounds. If we can get it down to 1 plus log s, then you get more to log t. But that, I've been trying to improve the number, but it seems a little hard. And again, I just want to reemphasize that can we extend these results to odd minors? So most of this new stuff works for odd minors, but it seems like it fails in one of the parts, and the same for list coloring. I couldn't get it to work. Most of it kind of works through. The Girau-Narayanan, they proved a version for list coloring. So most of it could go through, but I think it was the rebuilding the minor. I got a bit stuck on how to do that, how to preserve the high list chromatic number. So there's that. And just generally, could we color small graphs better, right? If we can eventually improve density increment, we're down to t log t. And then one big bottleneck will be, small graphs, can we color those even better? Currently, we're just using this t log t. So we haven't proved Hadwigers even for those very small graphs. So that would be of interest. And just generally a question that maybe even Sergey and Zizhi had kind of asked in their paper was, could we use connectivity instead of chromatic numbers? So here I really used it as a resource. I'll point out that Sergey and I, for the quarter case, in the list coloring, we'd actually proved kind of a stronger result that if you're t log t to the beta connected for beta greater than a quarter and no KT minor, then your actually vertices are small. So the number of vertices is t log t to the 7 quarters, which is very small, so you can just color it. So you could hope that some similar thing is true here, that if you're t log t to the 6th connected, no KT minor, the number of vertices is just small, so you could just use the small graphs lemma. But I wasn't able to do that because I couldn't figure out how in connected graphs to kind of find these right kind of layers, either these recursive layers or these sequential nesting. So instead using chromatic number to do that. So those are kind of my future directions. It'd be nice if we did all these things. There's a lot more work to do, but yeah, I think these are the nice questions for now.
Any questions? Would your results say anything about, say, fixed complete graph free graphs, like triangle free graphs? Hadwigers.
Yeah, so maybe it's right, maybe not. Well, yeah, I was debating, right? So there are these new results, right? There was you and Zednek with the triangle free improving. You've actually improved the independent set numbers.
Yeah,
right?
there are better results now.
Right, there's now better results, and for just fixed minor free. So I was thinking about those. So those will clearly, in the same way, improve the small graphs. So we can know how to color small graphs better than for triangle free, K4 free, etc. Unfortunately, again, the bottleneck is still just the density increment. Theorem is one. There's also a second bottleneck beyond that and small graphs, or third bottleneck, I guess, is in the recursion. So I use the log t for the number of layers. So we'd have to be a bit smarter if you want to get rid of the log t and the number of layers. But it would be very nice, yeah, if we could just prove that Hadwiger's holds for triangle free graphs, right? In the same way as Girth 5 is known for fixed complete free. And I think that maybe is attainable, but we have to maybe solve some of these issues first. That'd be good.
Thank you. Any other questions? Well, if not, I suggest we thank Luc once again. Thanks, Luc, for a great talk.